Okay, greetings. For today we are going to be learning about Hamming code. Now what is Hamming code? Now Hamming code is an error correcting code, and in this case we are going to be splitting our message into blocks. Actually, you can look at Hamming code as some sort of error correcting code that is classified as a block code, because in this case you are splitting your message or your bits into certain blocks, and then we are able to add some redundant bits. Okay, now these redundant bits are still the same ones that we are going to call parity bits, and we are going to see what to do after that. Okay, so Hamming code was developed by Richard Hamming as a way to maybe detect errors, not even maybe, to detect errors and actually correct them thereafter. Now 3 steps are followed as I had discussed earlier. In this case, number one, you calculate the number of redundant bits. Okay, that is step number 1. And then step number 2 is you highlight the position of those redundant bits, the position of our bits. So you can also say calculate, but you will see it's something that is pretty straightforward, so there is no much calculation that is there. And then number 3, you do get to calculate the value of the R bits. Okay, so we are going to follow those 3 major steps. Okay, now to start us off, we are going to start with step number 1, where we are talking about calculate the number of R bits. Now in this case, there is a formula that is used, and the formula in this case, I don't know why I just done that. The formula in this case is based on something very simple, where we are comparing the message bits and the redundant bits. And maybe before we go here, it's good to talk about the question that I have up here. I think I missed to mention that. And we are talking about us calculating the Hamming code given this message. The message in this case is 1011, and we are asking ourselves what is the Hamming code of that. So we aim to calculate the Hamming code of that message, which has 4 bits. Okay, so maybe before even we go to calculating the number of redundant bits, it's good to know how many bits do we have within our message. So we have 4 bits. Okay, you can see we have 4 items here, 1011, so those are 4 bits. Okay, so the formula in this case goes and uses the number of redundant bits and messages bits to be able to actually now come up with that. So we have 2 to the power of R. Okay, so I'll come back and do that, and then it should be greater or equal to M plus R plus 1. Okay, so these 2 is the one that I'm just going to make as a superscript there. Good. So that one. So essentially we are going to use actually try and error, where we are going to be using this formula. We already know what M is, because I've just said in this case M equals 4, because we have 4 message bits. Okay, so we're going to replace that within this formula, and then we are going to test numbers from 0 all the way to n, so that we can find the value of R. Okay, so now for R is the unknown. Okay, we don't know R, but then R can be any number from 0, 1, 2, all the way to n. So this is the reason why I'm saying we're going to be testing these numbers as the possible value of R until a point where this formula holds. Okay, so going by this formula, if we are to start us off and we assume that R in the first instance is 0, right? So if we are to take where R is equals to 0, we'll find that this formula is not going to hold. The reason why it's not going to hold is because whatever is going to be on the left will be this is 2 raised to 0. Whenever you raise any number to 0, you have 1, and you can see it's going to be not greater or equal to these other side. We already know what M is. In this case, M is 4 plus R is 0 plus 1, which is 5. So that does not apply. Now once you do this, okay, you keep on testing R being equals to 0, you test it being equals to 1, you test it equal to 2. You'll find that the point at which the formula holds is when R is equals to 3. Okay, because at that instance, on the left hand side we are going to have 8 being greater or equal to 8. Okay, so in that case our formula is going to hold at that point, because 2 raised to r, in this case r being 3, is going to be 8, and on the right hand side we have m, which is 4, plus 3, okay, that is 7, plus 1, which is 8. So that's the point where it's going to hold, and we are going to find that in this case our r will be given as 3. Now I should say that this form of Hamming code, where you have 4 message bits and you have 3 redundant bits, is one of the most common Hamming code that you find. We actually call it the 7-bit Hamming code. So it's one of the most common one, and I think to some level it also tends to show the origin of this, because this is a very long time ago when Richard Hamming was able to come up with this block mechanism of detecting errors and even correcting them. So these computers were not that advanced back in the day. So we have 7 bits in total, because we are going to be having 4 message bits as seen within our message, and then we have 3 redundant bits. So that takes us to our step number 2, in this case, where we need to know or maybe highlight the position of our bits. So the position in this case is usually the powers of 2. The powers of 2. So what this means is, after we have this message, which has 4 bits, and then we have the redundant bits, which are 3, we are going to be having 7 bits. Okay, simply put, let me try and use a very nice table here. I'm going to have 7 different locations, okay, that way, and maybe just to help, I'm also going to put an extra one that way. Okay, so we are going to have position 1. Okay, then because I want to make my work easier, I'm just going to copy and paste all over the place here. Okay, and I'll explain in a short while. So this is position 2, this is position 3, this is position 4, this is position 5, this is position 6, this is position 7. So the reason why I have 7 location is because, like I've said up here, we are having 4 message bits plus 3 bit redundant bits. Okay, so that gives us 7. So we have 4 place values. Okay, so we have that way, and as usual I'm going to start the usual name when this is the least significant bit and this is the most significant bit. Okay, so we are saying that the location of our redundant bit, because we need to know the location. Okay, we already know that there are 7 locations, but then we don't know where these message bits, the 1011, where they're going to be located, and where the R bits are going to be located. So first we must locate where the location of the R bit is, and then maybe the rest, the remaining locations, we can be able to fill them up with these message bits. So we have said that the location of the redundant bit is going to be at the powers of 2. Okay, so the powers of 2 in this case means that you are taking 2, I don't know, like it's that one, that is what I was looking for. So when it's the power of 2 is that way. Okay, so that will be the position of our redundant bits. Now in this case, my R again, okay, will be from 0, 1, 2, all the way to n. Okay, so in that case, when R is equals to 0, okay, so 2 raised to 0 again is 1. Okay, then when R, let me just take this one down a bit, then when R is equals to 1, 2 raised to 1 will be 2, and then when R is 2, 2 raised to 2 is 4. Okay, and then when R is 3, 2 raised to 3 will be 8. Right, so that one on and on and on and on and on. So obviously we don't have to go beyond position number 4, because the next position is position number 7, and our entire number of bits does not count for 8. Okay, the position 8, so it's not there. So we just stop at 4. Okay, so the first R redundant bit will be located here, so this will be R1. Okay, and then position number 2 will also have the second redundant bit, and then we're going to skip position number 3 because it's not a power of 2, and then position number 4 will be the third R bit, which we denote as R4, so that at least we can be able to designate its location, you know, within the naming. Then we go back and we remember that our message bit was 1011, so we just fill it in the orders which it appears. So in this case, position number 7 will have this 1, position number 6 will have this 0, and then position number 5 will have this 1, and then position number 3 will have the other 1. Okay, so you can see this is my message. I've just placed it in the order to which the digits appears. Okay, so that's how it is. So step number 2 is done. Okay, so we were just trying to know our position, and then the number 1 was calculating the number of redundant bits. Okay, then the third step is to calculate the value of the redundant bits. Okay, so before we are able to proceed to that, I would advise us we first take a closer look at what we've done so far. So I'm going to stop this video here, and then I'm going to come back with a second video where we are going to calculate the value of the redundant bits. Remember, the first step was to calculate the number of redundant bits, which we used this formula and we were able to do that. Then the second step was to know the position of those redundant bits, which we came to know that was the powers of 2, and we've been able to articulate and show it there. So the third step will be to calculate the value of this R bit. What I mean by that is, you can see we have generic identifiers R1, R2, R4. So we need to know their value. Is it a 0 or 1? Is R1 a 0 or 1? Is R2 a 0 or 1? Is R4 a 0 or 1? So stay tuned. That is what we are going to be doing in the next video.